Good morning. Welcome once again to this lecture. I hope you can hear me well. Today we are starting a new chapter on memory devices. And after this is actually the longest chapter, generally speaking, in this class. After this, we will do another chapter, a small chapter that is really important. And then we will focus on some projects and I'm looking at maybe in another 5 or 6 lectures that the main part of this course is over, and we are now really just preparing for exams and learning a few more things here and there. So you're welcome. We are going to start, although people are few. We look at memory devices. We know how important memory devices are to, for instance, computer systems. This is an example of or a block diagram of a computer. We have, I think you know this from your first year, we have the CPU. The CPU is really the brain of the computer that includes the arithmetic and logic unit and the control unit. And as part of that, of the computer, you also have memory. So these are really the most important bits within a computer: memory, control unit, and the arithmetic and logic unit. We've sort of looked at the ALU, with our look at how logic happens within the computer, how bits combined, and so on. Those are the processes that happen within the ALU. Then you have the control unit that controls everything, and then now we want to look at the memory. Now the memory is made up of two types of memory actually. As you can see here, you have your main memory, which is really semiconductor memory, and you have what we call auxiliary memory. And this auxiliary memory is for mass storage. So you have, for instance, magnetic tape, CD-ROMs, and so on. Those are part of auxiliary mass storage. But the main memory is made usually of semiconductors. It's very expensive, and so you're not going to have a lot of this memory in your computer. It's usually so expensive. But it's also the main memory of the computer. Most of the time, this is where the instructions are kept. So, instructions or programs to do with what operations, how operations happen, are kept within the main memory. The reason why it is expensive is because it's very fast compared to auxiliary mass storage. It's really fast, and it's made out of, it's a semiconductor type memory. Now, we've looked at how why we do digital communication. Digital, when you're dealing with digital information, digital data, it lends itself nicely to mass storage, and so you can keep it over a long time, which is not the case with analog information. And we've looked at some of the things that we can use to store information, chief among them the flip-flop. Okay, so this flip-flop that we looked at last in your first year, and we've talked about briefly this year, is an important data storage device or circuit within our memory. And it's usually what main memory is made out of actually, the flip-flop. We know that each flip-flop stores one bit. Now, a combination of these usually form registers, okay? And so a register stores a number of bits, so-called words, okay? So a register of like 4 flip-flops will store a 4-bit word. We call it a word because we expect that those 4 bits mean something together and not each one alone in isolation, but a combination of them mean something together. So when we say a bit word, we mean a combination of bits that need to remain together and need to be looked at together. Now, usually within the memory, you have a memory. I think you have seen memories. These are, integrated circuits, large-scale integrated circuits, or very large-scale integrated circuits. And within here, you're going to have a set of registers, okay? And you can pick out, as I said, these registers store information, words that are related, and they need to stay together. And so when you want to get information from this one, you need to specify which specific register you want to get your information from. And so that really gives us the idea of addresses. That means that each memory, part of the memory needs to have an address, or each register needs to have an address, and you can call that register addresses. These are some of the things that we'll be highlighting. And we know that we usually do two things in memory. We do something that we call read, okay? So when you are picking information from memory, we call that reading. You're reading information from memory. Now, when you read information from memory, the information stays in memory. You just take a copy of that information. But we also do something that we call write. And when we write information, we are storing information in memory. So if you copy a document of your flash drive and put it on your computer, what you're doing is you are writing, okay? We can, for instance, if you delete, really what you're doing is you're writing zeros into your info, into your memory. Now we are going to look at some of the terminologies that we use in memory before we look at some more details. And these are the terminologies that we can think about in terms of memory. A memory cell is a device or circuit that stores 1 bit, strictly 1 bit. So if you have a piece of circuit or a piece of device that stores at most 1 bit, that is called a memory cell. So each cell stores 1 bit. And an example of this one is, for example, our flip-flop, but we can use a capacitor as well. A capacitor can be used in the sense that, sorry, if it is charged, it is storing bit 1, and if it is uncharged, it is storing bit 0. And so also on CD-ROMs, we are going to see how CDs actually work. So we are going to see how information on your compact disc, CD's compact disc, works, but it doesn't work in the sense of a flip-flop. You don't have flip-flops on a compact disc, but usually you have a certain spot where you either put a hole or you leave it blank to mean either bit 1 or bit 0. So that little bit of space on the CD-ROM is also called a cell. The memory word is a combination of bits that are stored together within a register. And that combination of bits could be 2 or 4 or 8 or 16 or 32 or 64 and so on. These words are usually combined together, and the word needs to stay together. Those bits need to be together because they are interpreted together. So that creates a word. Now, a byte is actually an 8-bit word. Okay, so an 8-bit word, which everyone I know for sure knows. Enable is a 4-bit word, just while we are still on this. Okay, but a byte is an 8-bit word, and so we can, if we have a combination of 8 bits, we can just say we have a byte. Capacity is number of bits stored in memory. Okay, so if you have your memory like this one, if we have stored 4 bits, usually each of these registers in memory, each of these registers will usually be the same size, okay, in terms of word length. Okay, so if these registers are storing 4-bit words, all of them usually will be storing 4-bit words. I'm going to give an explanation why. This is not to say that in a computer you only have guys, switch off your videos. Brolin Mutumba, we can see you are in bed. you should switch off your videos so that you do not distract us. Yes, I'm now distracted, you see. So yeah, so I was saying that when you have one piece of memory, the registers that are in there will usually be of the same size. So if they are 4-bit registers or 8-bit registers, all of them are that size. This is not to say that one particular computer uses all similar size registers. You might have one piece of memory in the computer with 4-bit registers, and in another piece of memory, a separate piece of memory with 8-bit registers. Anyway, so for instance, if this stores 4, then our expectation that is this one also stores 4 and 4 and 4, and so this one will usually be 24 bits. We can say that our capacity of this memory device is 24 bits. Now let's assume that we are storing, let's say capacity, we have stored 1024 words. Each word is 8 bits, or each word is a byte. So then we can simply say that for each of these 1024 words, each one has 8 bits. So our capacity is in fact 1024 times 8, which is that 819? I don't know, 2. Let me see. Yeah, 8192 bits. That is how you describe your capacity. Now we like to say that for a memory like this one, that capacity, we can write capacity as 1024 times 8. Okay, so that this just tells you that these are the number of words, those are the number of bits per word. Now, with most memory, the number of words tends to be a multiple of 1024. So we can usually break that down into 1024 multiples. And we know that 1024 is equal to 2 to the power 10. Okay, so 1024 is actually 2 to the power 10, and we can call this k, actually that is 1k. So 2 to the power 10 is equal to 1k, and so my capacity here then can therefore be described as 1k by 8. That means if my capacity was 4k by 8, this is essentially equivalent to 4 times 1k, which is 1024 times 8. I don't know what that gives me, times 4, which gives me 32 768 bits. So this is how we express memory. Wherever we have a chance, we can express it in terms of k. Now, as the large scale integration and very large scale integration became possible, we started to make memories of really very high capacity. And so we also brought, this k is like kilo. Okay, now usually we associate the kilo with 1000, but in terms of memory it is 1024. There shouldn't be any ambiguity because we are with digital systems, we are working in powers of 2. We also have the mega. We can say the meg. Okay, so the meg, we say 1m, which is like 1 million, is equal to 2 to the power 20. But 2 to the power 20 is not exactly 1 million. It is something that is a little bit more than 1 million. Just like the k is not 1000, but something a little bit more than 1000. And so this is 1048576. And so I can say that my memory is defined by 8m times 16. What I mean is that it is really 8 times 1m times 16, and the capacity of that will be 134 217,728. You're looking at 134 megabytes. about 134 megabytes. In the past, when we megabits, sorry, not bytes, bits. If it was megabytes, we would have multiplied by 2, because this 16 is really 2 times 1 byte. So a megabyte and a megabit, totally different things, and I think this is something that you already know. We can, in fact, continue with this discussion on capacity, and we go to gigabytes or gigabits. And this is 2 to the power 30, which is in the billions, in the gigabit range, to which is something like 1 billion, sorry. 073 741 824. Okay, 824. So if your capacity is that big, then you don't have to force it to express it in K or M. You can express it in G. So I can say that 4G times 4, I'm looking at my capacity written as 4G times 4. This is the number of words, and we know that each word has 4 bits, and so you can continue with your calculation and find the capacity. So really the capacity is the size of the memory, and it is the number of bits that you're able to store. That's why you have flash drives of 4 GB, of 2 GB, of 16 GB, 32 GB. So all of that is already apparent to you. But I think what's important here in class is to understand how we express the capacity. So if I come and say 16K by 16, or 2M by 4, these need to be very clear to you. You shouldn't have to deal with any ambiguity in that context. Let's go back to our terminologies. Density is also something that actually describes capacity, but it describes capacity in the sense of per unit size or per unit space. And so when we say that one memory device is more dense compared to another, we mean that in the same size of space or substrate, one memory device stores more bits. The density, something that is dense. I think this is an English word, actually, you should know it. If something is more dense, it means you have packed more things within the same space. And usually this comes from the capacity to miniaturize the memory cells so that you can have more memory cells in the same space of storage. Ian, the notation is very easy. It is capacity is equal to number of words times word length or word size. So that the size of each of these words. So if it is 1K by 4, it means I have 1024 words, and each word is 4 bits. So if I want my total capacity, I can get 1024 by 4, which is 4. 4096. Yes. Ronald, on density, I meant, so let's imagine we have same space of, let's say this is, let's assume that is the same size of substrate. But in here, I'm able to store a capacity of, say, 1M by 4. Here, I'm able to store a capacity, say, of 2M, as long as it's greater. So the word length is the same, but you can see that the number of words are more. We say that this memory is denser. It's denser because we've been able to pack more bits in the same size of substrate as opposed to this memory. And so the idea of density speaks to capacity as well, whereas it does not specify the exact capacity in terms of bits. If I tell you that this memory, this memory device is denser than this memory device, if you want more capacity, you take the denser one. I think you've seen flash drives that are the same size, but one is 16M, one is 16 GB, another one is 8 GB. Just means one is denser than the other. But we need to be careful because for those capacity, you know, flash drives being the same size is not calculated on the share outside. You have to look on the board and see the size of the memory. Usually there is a black IC there. But that's, yes, that's in terms of density. That's what I mean. Address, yes. Address, I've already said that in memory, the only way we, you know, your memory is going to be packed with a lot of devices, memory devices. If you have 16 by 4, you're going to have 16 registers. Each register will be 4 bits. So something like this, those are 4. You're going to have another line here. It doesn't matter how you arrange these, but we are going to see actually that they are arranged in terms of some form of array. And so you have, let's say this is your memory, 16 words. So this is 1 word, 2 words, 3 words, 4 words, and so on. Up to 16, each one has a word length of 1, 2, 3, 4. Now, if I want information, so let me say this is maybe 1, 2, 3, 4, 5, 6, 7, 8. If I want to access register 8, I want to access register 8. Either I want to read in from it or I want to write into it. How do I access it? We need an address. So we need an address format that each address can, that each of these registers has a unique address that can uniquely, or that can actually identify it to the CPU, because usually it's a CPU seeking this information. So the concept of address is that each memory has addresses that uniquely identify it. We are more interested in identifying words. We are not interested in identifying bits, because I said that a register is already like 1 unit and those bits will always be accessed together. And so we only need to identify the register, and each of these boxes here is a register. Now we know that 16 is equal to power 4, okay? So it means that I need 4-bit address code to uniquely identify each of these registers. And so I could say that this will be uniquely identified by address 000, this one 0001, that one 0010, that one 0011, and so on and so forth until I reach here where I can use 1111. So you can see, for instance, here that you have, actually this is probably, so if you look at this memory, it's a very simple memory, which is 8 words, okay? And word 0 to word 7 is 8 words by, you can see that each word is, we don't know the word length here, we've not been given the word length. It could be 1, it could be 4, it could be 8, it doesn't matter. However, we have our addresses. This address will identify word 0, that address will identify word 1, all the way to this address 111 addressing identifying word 7. And so let's say, for instance, that I want to read, I will apply my address. I want to read from register 7, which is that last one. I will supply my address 1111, sorry, 111, this one is not there. And then when I'm reading, the information will appear at the output. So you could say this is the input, that is the output. This information will appear at the output, and it will be sent to the CPU, which is the one reading the information. So addresses are very important, and you really cannot deal with memories if you do not understand addresses. Okay. The read operation, as I've already mentioned, is there's information in the memory and you want to read it. You want you want to move it. You want a copy of it to take it to the CPU, maybe to use it in some operation. So we call it you are reading. Okay. Now a copy stays in memory. So when you read, it doesn't mean you take the information as if you are cutting it. You are really just copying a copy of that, and the information remains within memory. We also call this the fetch operation because you are fetching information from memory. The write operation is different. When you are writing information, it means you are getting information from outside and you are writing it into memory. So that means that when you want to write information in memory, you need to identify the address where you want to write that information, and then you need to provide that information to the memory device. Once all of that is done, the memory device will be able to identify the location based on the address you've provided, and then move that information into memory. So as opposed to the read operation, when you write information in memory, the original information in that memory will disappear and you will store the new memory. We also call this store operation. Okay. Yeah, we also call it the store operation. Savannah, my audio is faster than the video. I don't know. What is the experience of others? Okay, so what should I do? Let me. I actually don't know what to do. So my audio is faster than the video. I don't know if this is on. Okay, so it means you hear me before you see what I'm talking about. Is there anybody with a better experience where things are in line, or all of you are facing the same issue? It seems there is nobody with a better experience. Maybe I stop writing and we just talk like history. Would that be better so that you're not distracted? Okay, so the other issue I had was whether you could just log out and log back in. The issue is I don't see how that helps. If that sounds like a waste of time, and of course everyone would go off. Let me just log off and then we'll get back on. Just 1 minute. I'll wait 1 minute, everybody to come back on. Leave meeting. So I'm going to make Maureen